Good day everyone, and welcome back to my YouTube channel tonight. If you have been watching my videos, you see that we have started a discussion on a transistor amplifier. In the previous videos where I did the implementation of the common emitter transistor amplifier using the potential divider biasing method, you must have been so familiar with the circuit diagram that you see on the board, and if you equally look at the values, you see that the same values, the values I used there is still the value that you are seeing in this circuit on the board. So which means this is a continuation of the discussion. Now you in your laboratory, you may be asked to plot the frequency response curve of this particular transistor amplifier. Now, what do we mean by frequency response? Is that the range of frequencies where the transistor can operate. Because when you apply a signal, you know AC signals have frequencies. So there are certain frequencies, like for example, this system is an audio amplifier, and audio frequencies ranging between 28 and 20 kilohertz. So any frequency that goes beyond certain frequency bands that this amplifier has been designed to operate, it will not you will not have a constant gain. You not have the gain. There will be a fluctuation in the gain. It's either the gain reduce or there's an excessive increase in the gain. And one problem with the excessive gain is noise. Once the gain is too much, then there's noise will set in. That's why they normally in the amplifier design there's a procedures we normally call a negative feedback. Negative feedback is a process through which we try to feed back a portion of the output of a particular amplifier back to the input in order to control the gain, so that the gain will not be too excess. So in this system, I want to quickly show you how you can find the frequency response curve. From the frequency response curve, you'll be able to see the frequency, the range of frequency where this guy can operate. So let's see how we do that. You go to probe on your Proteus menu box or menu bars. When you look at probe, you pick a voltage probe, then you put it at the output like this, just like what you are seeing here. Click on it. Once you have done that, so we want to plot the output of this amplifier with respect to the frequency. That is, you know what you set here as the input, that is with respect to the input frequency. Remember, we set 1 kilohertz as the frequency, but we want to carry out a kind of analysis. We call it AC sweep. We want to carry out a AC sweep as in at the range of frequencies, what happens to the output signal. So that's that about that. So when you go to that, then you click on graph mode. You click on graph mode, you go to frequency, because what you want to do is frequency response. Drag it on the screen. You drag it on the screen to draw a graph. Then you go and click the probe. When you click the probe, you drag it to the probe and drag it to the graph. When you have done that, right click inside the graph and go to edit graph. When you go to edit graph, the reference point chooses as root, the root that is C1. Then the start frequency, you can say let's start our iteration, our frequency sweep from 10 Hz, and I want to get to something around 3 million or 3 megahertz. So we want to carry out a decade sweep. The number of interval, leave it as 10. Click on OK. Simulate. Press space bar on your. When you press space bar on the graph, you see the frequency response curve will be shown. You can right click to make it a bit bigger. You can say maximize window. When you maximize window, you see now when you look at this curve, you must have come across a kind of a curve of this nature. This is what we call the frequency response curve. Now, at the center, there are three key frequencies that we must understand about this frequency response curve. Number one is the mid frequency, where we have the highest power. When you look at this system, the gain of this system is around the highest gain that we could see here is around the 11.7 decibel. We have seen that naturally this frequency response has converted our gain to decibel. It has converted our gain to decibel. So when you click on cursor to get the highest frequency, like everywhere around here is the highest. These are the highest points. If you take a look at what you are seeing here at this side of the graph, you see the value 11.7 decibel. You see that as the cursor is moving, the frequency is changing, because the x-axis of this graph represents the frequency, while the y-axis represents the gain. So at this point, this is where we have the maximum power, where the maximum power of this system is contained. So now in the analysis of a frequency response, we calculate 70% or 70.7% or 0.0707. That's 70.7, 0.70707, which is the same thing as 70.7% of the peak value. Like for example, let's say I want to calculate the peak value is 11.7. So let's say okay, let me use the Excel sheet. So peak value, if our peak value is 11.7 decibel, 11.7 decibel. So 70.7% of that, 70.7 divided by 100 multiplied by 11.7. So let's see what that will give us. So if you take your calculator, let me get my calculator here. Okay, my calculator is not coming up. Let's get the calculator. My system is running pretty low these days, so let me get the calculator. Okay, so the calculator is here. Let's see what that value is giving us. Let's see what that value is giving us. Okay, we have more than one already. Okay, so 70.7%, that's a 70.7 divided by 100, that's a 0.70, then multiply by 11.7, which is the peak value, the peak gain. That's 8.2719. So when you go to that's 8.2719. You look for it on the graph. So 70.7. So when you take the cursor, try to drive it around. So the half power point, you know, at this point is still peak. So 8 points. Be checking just be observing the value of the gain at this x-axis. Be observing the value. You see that a point will be reached when the value will change. You have seen that it was 11.7. that's the highest. The moment the value change, that's a lower cutoff frequency, 11.6. so this point is our lower cutoff frequency. So what is the frequency that corresponds to that? 18.8 Hz. So which agrees to what the theoretical understanding about an audio amplifier. You know, we say that audio signals are between 20 Hz to 20 kilohertz. 20 Hz, 20 Hz. So when you look at 18. So it means once the frequency is getting lower than 18.8 Hz, the amplifier will not be able to amplify it. Then let's check that same thing at the right side. So 70.7, 11.6. So what do we get? So 11.7, 11.6. So 2.02 mega ohms, so megahertz. So that is the upper cutoff frequency. Then to find the bandwidth is just a summation of upper frequency minus lower frequency. So the bandwidth of this system will give you f2 minus f1. So f2 is 2.02. So bandwidth equals to f2 minus f1 minus f1, which is a 2 point what? Let me check the value again. 2.02 megahertz, 2.02 megahertz, 2.02 megahertz minus 18 point what? I think 18.2. So when you do the subtraction, you get the value of your bandwidth. So that is how we in a very fast way to work out the frequency response of an amplifier. So this is a very simplest way. So there are difficult ways. If you like difficult things, you want to go through the difficult part. What we do by the difficult aspect is we iterate manually. Let me go back to the schematic. If you want to go through the difficult part, you iterate this value manually. When you have set 1 volt or 0.5 volt as the case may be, and you begin to change the value of this frequency one by one, and you'll be observing the waveform. And you change it one by one, you observe the waveform, then you form a table of this nature, frequency response curve. When you table, frequency response table, you draw the frequencies, you draw the gain. That is the gain is a V output over V input. When you have done the gain, then you find the gain in decibel. The formula for finding gain in decibel is 20 log AV, which is 20 multiplied by logarithm of voltage gain to base 10. So I've used the formula here. I think I've inserted the formula 20 log 10. Then E6 represent where the voltage gain is. So once you have done that, you can now plot the graph of frequency against the decibel. So but that is pretty long. So I think the approach I use using the automated system is far better, and it can give us a wider range of frequencies. So that will be all for now. So if you have any question, please kindly reach out to me on the comment section or using my official email optiforclaim@gmail.com. So please do well by subscribing to this my YouTube channel, like, comment, share, and recommend to your friends. Thank you, and bye for now.